I think
Does anyone don't understand Chinese?
Andrew Fudan, not sure.
Oh, okay.
Cool.
Yeah, Andrew phone.
Okay. It's okay. I mean, we're putting this on YouTube anyways, so I could do it in English. It's okay. Okay. Do this. All right. Let me. I think I'm covering it. Okay. I've not done all of these, so this one and this one I've not done. If anyone has a solution to these, please welcome. And I'd like to think of this as sort of an open forum. But I can tell you where you could look this up. It's theorem 330, and then in this form, it's closer to corollary 331 in the in this paper, the even ordinals paper. It's slightly longer. If I have time left at the end, I can maybe say a little bit about how this paper starts. You know, the relevant concepts. I've only got that far. And maybe some guesses as to where the inspirations for and the motivations for these definitions come from. But let me start from the top, the easier ones. So the flat pairing function, this is kind of routine. If you read, I think the Kuhn book is there as well. The point is, I'm not gonna write out the full proof, but the point is, so in the Kuratowski definition, right? So the ordered pair XY is defined to be, if I remember correctly, this guy. And the problem is rank of this pair is greater than the let me write max of rank of X. So it's going to be, this object is going to show up later than X and Y. So you want something that shows up at the same time. So this Quine-Rosser pairing does the following. So you want to define the pair X and Y to be this set. I'll explain the notation later. All right, so X0, Y1. Well, basically the definition is like this. But the point is, look at X, right? It's got a bunch of members. What you do is remove for each of these points. What you do is you remove you add 0 to it as an element, and then move other natural numbers by 1. So up 1. Right, and then for Y, what you do is, okay, for any element in Y, you just move all n in this element that is a natural number to n plus 1. Right, and then the point is, from this set, you can recover, maybe not recover, you could let me say this, you could decode which elements come from X, right? And this is done by checking whether 0 is in that element. Right? And similarly for Y. Right, and you just check whether 0 is not in it. Why is this pairing flat? The point is if X is in V alpha, then this means X is a subset of V alpha minus 1. So if alpha is successor, right, or X is subset of some V beta if alpha limit beta less than alpha. Right. And so for alpha greater or equal to omega, all the natural numbers are in it. So all the natural numbers. So omega is a subset of V alpha. So this operation of modifying stuff so that 0 gets in there or 0 doesn't get in there. This operation produces a set that is that gets into the V alpha, that gets into the von Neumann hierarchy at the same time that X does. Because if you think about the cumulative hierarchy, the iterative conception, you're basically collecting stuff that's available at a certain stage. Right? If you want to go from V alpha to V alpha plus 1, you just look at all the stuff, the ingredients, if you will, available on V alpha and then collect them. But then X is available. All of the things in X are available at this V alpha minus 1, and so is omega. All right, and so yeah, and so this operation doesn't raise rank. All right, so the result is that the set the Quine-Rosser pair. So let me Quine-Rosser pair has rank max rank X and rank Y. All right, so the point is right, to get this pair, you just wait till whichever has higher, say X has higher rank, you just wait till all the ingredients are available for X are available, and then you cook something that's slightly different to get to this pair. Okay. All right. And let me move to something that's perhaps more interesting. This second problem. Oops. Here. This is similar to Suzuki's theorem and uses a very similar trick. So the claim is if lambda is limit, so limit ordinal, then no elementary embedding from V lambda to V lambda can be definable from parameters in V lambda. Right, so this is very much like the Suzuki proof and the Suzuki theorem that says no elementary embedding from V to V can be definable from parameters in V. Want to do something very similar, and that is to look at all the possible elementary embeddings that could be defined using all kinds of parameters. So proof. Suppose not. So we let this formula phi taking two variables and some P parameters define an elementary embedding J going from V lambda to V lambda. Now, let's pause a moment and think about how you might want to do this. So if J is parameter free definable, then this is very easy, right? You just use the routine reflection argument. You say something like, okay, V lambda thinks, kappa is the least ordinal moved by J. And then V lambda is going to think J kappa is the least ordinal moved by J, so contradiction. But the problem is this only rules out parameter-free definitions of J, whereas we're dealing with something with parameter. So second scenario is when, say, what if P is fixed by J, right? Namely, J of P is P. Right, then we have a similar situation, namely V kappa is going to think, I'm sorry, not V kappa, V lambda is going to think this critical point kappa is the minimum ordinal moved by, let me write the definition, by the function defined by phi x, y, p, right? And then elementarity, J kappa is the least ordinal moved by the function defined by phi x, y, j, p. Right, but in this pretend scenario, we have jp is equal to p, so this is p. Right, so again, contradiction. Right, since truly the same function we were defining here, so this reduces it to the parameter-free situation. But we don't know whether P is fixed by J or not. So, but this gives an idea as to how we might go about this problem. So the point is, excuse me, the point is you want to look for some property that is fixed by elementary embeddings of P, instead of arguing that the elementary embedding fixes P itself. So you want to say P has some property that may be easily definable or something like that, and that elementary embeddings are gonna preserve their property. So okay, so let's follow Suzuki and use this trick. So the property, as you can see, is what I would like to call defining an increasingly elementary embedding. So I will show you what it means in a moment. So, okay, so use Suzuki's trick. So use Suzuki's trick. Define the set C to be all the possible parameters that define that define elementary embedding. So this Q such that phi x, y, q defines an elementary embedding from V lambda to V lambda. Okay. Now, let kappa 0 be the least critical point. Let me say, so if an elementary embedding is defined by this formula with parameter q, let's call it jq. Right, so it's the minimal of the least critical point moved by these jqs. So you've all seen this in the lecture yesterday, so shouldn't be anything new. And then let Q0 be let me think, be the parameter used in defining the J we suppose to be definable. What I mean is here, we're supposing that some elementary embedding is definable. So what I'm really saying is, instead of writing P, I write Q0 just to be consistent with all the notations. Okay. Now what you do is, this Q0 is going to be in some V beta. So we're going to use this V beta later. What I want to do now is I'm trying to pinpoint the property that this Q0 has that's going to be preserved by elementary embeddings. So for n less than omega, for any natural number, we say Q in V beta. So I'm only looking at parameters in V beta now. Is n good? Oh, sorry, I think I'm covering some stuff. Okay, so n good. If and only if, so this is the definition. If and only if JQ, right? Remember, this is the elementary embedding that gets defined by using Q as a parameter. If only if JQ defines, I mean, let me just say JQ is an elementary embedding from V lambda to V lambda, but not fully elementary. It's only sigma n elementary, right? So partial elementary. So if you're n good, then you define a elementary embedding that's only elementary with respect to sigma n formulas. Okay, now so define an to be the following set. It's all the parameter sets from V beta. Remember, V beta is where Q0 lives. Now you want all these parameters with the same rank as Q0. That is n good. Q is n good. Okay, so an collects the n good parameters. All right, so now you observe an is going to be in V lambda, right? Because it's a subset of V beta, and V beta is below V lambda, and lambda is a limit. And also each an is definable over V lambda from parameter beta. And the point here is that, so point sigma n truth is definable. So sigma n truth in V lambda is definable over V lambda. Right, so Tarski's theorem only rules out full truth, but partial truth, no problem. You could define that. And so this is, so an is defined by something like Q is in an if and only if phi x y q defines and sigma 0 elementary, sigma n elementary embedding, and Q is in V beta, right? This is where you use the parameter beta. Okay, something like this. So what does this tell us? AN being definable, this tells us that JQ0, so since JQ0 is, let me write sigma omega, so fully elementary. JQ0 of AN intersects V beta is going to be AN for all n in omega. Right, and the reason is it preserves this definition here. All right, JQ0 is fully elementary. So whatever you use to express sigma n elementary, that sentence gets that predicate gets preserved. Okay, so when you stretch out AN above V beta, you keep whatever's below V beta fixed. Right, it doesn't matter where JQ0 moves V beta. So you could try and prove this yourself. Not very hard. Let me see. So so let me isolate this fact here, and then there's another. So now we consider. So consider the sets A1, A2, A3, A4. Consider this sets. Right, these if you think of them as coding properties, right? This is the property of of parameters that say okay, a parameter defines a sigma 1, sigma 2, sigma 3 elementary embedding from V lambda to V lambda. So now if you look at their intersection, let me write A for the intersection of the ANs. Right, first notice that this is not empty. Why? Because well, Q0 is in there. Right, because Q0 defines a fully elementary embedding. So the elementary embedding that's defined by Q0 is going to be, sigma 1 elementary, sigma 2 elementary, sigma 3 elementary. Okay. So now also note, oops, that this sequence AN for n in omega is going to be in V lambda, since V lambda is a limit, right? It's in something like, I don't know, V beta plus 3, depending on how you code functions, right? Because all these ANs are subsets of V beta, right? So they show up, a few steps after beta. So this tells you that so this tells us that JQ0 of A, right? Again, this is the property that I want, that Q0 is going to have. That's going to be preserved under the embedding. So what do I mean? So if you apply JQ0 to the sequence A, by elementarity, that's going to be equal to the intersection for n less than omega of J of the ANs. Right, this is just by elementarity, and also we observe that A is in V lambda, so it's in the domain of JQ0. But then this implies that Q0 is in JQ0 of A. Right, because this follows from here. Right, when you stretch, when you apply JQ0 to ANs, you stretch it, but whatever's below V beta, you keep it fixed, and Q0 is below V beta. So now that we have this property A, well, we could carry out the reflection argument at the beginning that we wanted to do. So finally, V lambda thinks that there exists some Q in JQ0 of A, such that the critical point of JQ is below J of kappa 0. Right, so by elementarity, pull it back. So V lambda is going to think there exists some Q in A such that the critical point of JQ is less than kappa 0. Right, but this is a contradiction because kappa 0 is least such. So it's really, as you can see, a reflection argument coupled with the Suzuki trick of considering all the possible parameters. Yeah, so this finishes the proof. Okay, and this next one here, I'm not sure if I have this correctly. I did it in a hurry, so we'll see. So now, so the setup is this. So the setup is as follows. So J V to M is elementary. And there exists some function mapping Y surjective onto X. So this means onto. And we're supposing that J image of Y is definable over M from parameter P and some parameters rams in J in the range of J. Okay. And what we want is to give a definition over M with parameters like above. The definition is of J image X. This is my crude attempt. So let me see if this works. So we observe. Okay, we suppose so. Let phi X P and then J of something define J image Y over M. So let's see what it means for something to be in M. It means, well, X is in, to be in J image of Y. So X is in J image of Y if and only if there exists some little y in Y such that X is in J of little y. This is definition. And then by our definability assumption, this holds if and only if M satisfies this formula of when you plug in X. Okay. So we have this. And then you use F. So here's one, I guess, motivational point, or what you might want to call it, so general lessons or rule of thumb. So surjections are some kind of coding scheme. So whenever you see a surjection, you think, okay, there's something that I'm coding with this surjection. So let me see if this works. So now we have f surjects y onto x. So j of f surjects j of y onto j of x. But then j of f restricted to j image y is a surjection from j image y onto j image x. I haven't checked this part. I think it's true. Right. And then you could define, so using this observation, you just define, so for A, we observe A is in J of X, if and only if there exists some little x in big X, such that J of little x is A, right? And then this holds if and only if M thinks that there's some set X, I mean, some set S, such that phi of S, P, and then whatever parameter that's in range of J holds. Right, and such that A is equal to J of F of S. You know what I mean. So, so there's some unique S such that, and then to say A, well, this technically this should be A here, right? So yeah, and this follows from the fact that J of F is surjective. So I haven't checked this in detail. I might be missing something obvious, but yeah, I think that is yeah. So maybe let me write half a finish proof symbol. So for maybe QED. So yeah, so like I said, I haven't done these last two, but I can say a little bit about the setup if you try to read the paper even ordinals and the Fudan inconsistency. The point is, so I guess let me get a different color. Main tools in the even ordinals paper. And of course, there are many main tools, ultrafilters and whatnot, but in terms of these problems, is to have surjections and surjective images. All right, so the setup is, so these sets are going to be relevant for this paper. So given a set X, we define what do they right? So I think it's curly H of X to be the following set. It's the union of all the sets M such that M is transitive. And M, now this means, okay, I'm going to explain what this means when I finish writing this for some S in X. This means that there is some surjection going from S to M. Again, the context is ZF, so we're not assuming choice. So now a fact that you can prove in ZFC is, okay, I haven't finished defining. Okay, let me define one more thing before I, okay, now H sub alpha is equal to H of V alpha. Right, so it's anything in V alpha, it's a union of all transitive sets that could be mapped to surjectively by something in V alpha. Let me write this curly H. Okay, now a fact that you could prove in CFC is that the H, curly H, okay, so for regular cardinal, I think it gets more general than this, but let me just state the version for regular cardinal. Regular cardinal kappa, the H sub kappa that they defined is equal to the H kappa in the usual sense. Namely, this is the set M such that the transitive closure of M has cardinality less than kappa. And the reason is that in ZFC, when you could be subjected by something below kappa, then, okay, let me write, so point. In ZFC, surjection, injection, really the same thing, since you have choice and everything's well orderable. So if M is less than or equal to, in this star sense, in the surjective sense, some alpha less than kappa, then the cardinality of M is going to be bounded by alpha. Right, and whereas this is defined by using injection. Since everything's well orderable, so yeah, this is a pretty easy fact, so not hard to get. And the point is, so when you have these sort of ZF analogs of these H kappas, another main tool, another main setup. So main setup is the following. So fix infinite ordinal alpha. So we could get well, we can define a partial surjection. They write it as capital phi sub alpha, which goes from V alpha to H alpha surjective partial. So when you see this, something that should sort of, I mean, if you've seen something like this before, something that should be jumping at you is, well, first they define something, right, that's equal to H kappa in ZFC. So that's a hint that intermodal concepts are going to come into use. And then the second giveaway is this defining a partial surjection. Right, so the effect in that's useful for fine structure theory is that for each limit ordinal above omega, there is a sigma 1 with parameter in L alpha map from alpha surjection onto L alpha. Right, so here's a fact from in the model theory. the point is that, again, remember the rule of thumb, whenever you have some suggestion, you think, something's being coded. Here, it's roughly the same idea. In intermodal theory, L alpha could be coded in a simply definable way by this ordinal alpha. Right, so this is really, this phi alpha that we will be defining is really what's the opposite of line structure, like coarse structure analog of this, at least from how I look at it. Okay, so let's try and define this coding scheme, right? This partial surjection. So how do you define this? So to define phi alpha. Right, so if x is in V alpha, we write R sub x for let me do this. So I need another definition. I'm sorry. So write P from V to V cross V for the inverse of the Quine-Rosser pairing. Right. So the Quine-Rosser pairing goes from an ordered pair to a single set. So this is going the other way. So each set is thought of as some code for a relation. So, okay. Now we write Rx for P image X. So the idea is Rx is the relation that X codes. Right. We're now looking at each set X as a code for some binary relation. Okay, and write dx for the field of Rx. So what's being related? So the domain and range of this relation. Okay, so we define E alpha to be the codes for well-founded relations. Okay. Now, so if X does code a well-founded relation, then write pi of X going from dx to some mx for the Mostovsky collapse of dx under the relation Rx. Okay, so this mx is some set that is transitive. Okay, so now collecting everything that we defined so far, we write C alpha to be the set of ordered pairs x, y, such that x is in E alpha and y is in dx. So what is the intuition? The intuition is right from, so C is going to be an ordered pair, a set of ordered pairs. From the left coordinate, you have the answer to the question, what are the well-founded relations? It's coded in V alpha. And the y is going to tell you what's being related. Right, so that's intuition. Okay. Now for x, y in C alpha. We define phi sub alpha of x, y to be this pi sub x of y. Right, and then what's left to check is range of phi alpha is really the union of the x's in V alpha, such that m x. Right. But then if you look at the definition, right, this whole thing is just H alpha. So it's just a surjection. And it's partial because not every x holds a well-founded relation. So the point is, you look at V alphas and V alphas, look at the V alpha, right, for the particular alpha that you picked. And that V alpha is going to contain enough codes for the order types of transitive sets, right? So you just map a code of transitive sets over to, remember, phi is supposed to be a function going from V alpha to H alpha. H alpha you get by unioning over a bunch of transitive sets, right? So yeah, so you just look at the codes for the order types of these transitive sets, and then you just map these codes onto whatever transitive set they define, or the elements of these sets. Okay. And then maybe one last thing, in case you want to read this paper, is this J star. So fact, if J is an elementary embedding going from V alpha to V alpha, then this function J star defined by J star, it takes as input something in H alpha. Okay. And then we'll do the obvious thing, right? So it's like in algebra where you are trying to define homomorphisms and stuff. This J star, which goes from H alpha to H alpha, is also an elementary embedding. Right, so this involves some tedious checking and also getting a good handle on the definition of things involved. So take some time, so maybe I'll leave you to it. Right, so there's something else that you could do with J star, but I'm going to stop here for today. I think I've said enough. So if I were to do this this problem here, I would, following the hint in the paper, I will probably start by defining all these. So yeah, we haven't really lost much by me not giving you the solution. So yeah, so that's all I've prepared. If anyone has any questions, or if you have a better idea of how to do these, please feel free.
Okay, thank you. So Jason, maybe you should mention the last exercise has been updated.
Oh yeah, so I think it should be there's an additional assumption here. Yeah, thank you. I forgot. I'm showing you the old version. So yeah, you need this additional assumption.
Yeah, okay, thank you. And we have updated on our website. So if you like, you could re-download the exercise 3.
Yep.
Okay,